Today's notes are going to be on trig functions of any angles. In order to complete these problems, we must first look at the diagram on the right of your page and make sure that you understand each part of it. So to begin, we're looking in quadrant number 1. In quadrant number 1, all of the trig ratios are positive. That's the original trig ratios, sine, cosine, and tangent, and their reciprocal trig ratios, cosecant, secant, and cotangent. In quadrant number 2, we have two trig ratios that are positive. Sine is positive, and its reciprocal, cosecant, are positive. As we move to quadrant number 3, again, only two trig ratios are positive, tangent and its reciprocal, cotangent. And in quadrant 4, cosine and secant are the two positive trig ratios. To help you remember this, you can use the mnemonic device A, S, T, C. A standing for all trig functions are positive. S means that sine and its reciprocal are positive. T means that tangent and its reciprocal are positive. And C means that cosine and its reciprocal are positive. To help you remember A, S, T, C, we use the phrase all students take classes. Some other things to be aware of for your 4 quadrants on the right is what the reference triangles look like in each quadrant. In quadrant 1, your reference triangle stems from the origin, the hypotenuse or terminal side of your angle shoots out into the quadrant, and then a vertical line takes you back to the x-axis. For this triangle, both your opposite side and your adjacent side will be positive because I'm moving a positive x direction along the x-axis and a positive y. In quadrant 2, the reference triangle again shoots out into the quadrant and then a vertical line down to the x-axis. In this quadrant, my opposite side is positive and my adjacent side is negative because I have moved towards negative x values, but then up for a positive y. In the third quadrant, the terminal side shoots out and then back up to the x-axis. And in this example, the adjacent side and the opposite side are both negative because you've moved to the left and down, both negative x and y values. And lastly, in quadrant 4, it shoots out into the quadrant and then back up to the x-axis. In this example, my adjacent side is positive because I've moved to the right, but my opposite side will be negative because I'm moving down towards negative y values. If you have all 4 reference triangles drawn on one graph, they form a bow tie shape. You always want to remember that your reference triangles go out into the quadrant and then back up or back down to the x-axis. You will also be given examples that will contain either degrees or radians, so it is important to know the location of the degrees going along the 4 quadrants in both degrees and in radians. So radians is pi over 2, pi, 3 pi over 2, and then all the way around 360 degrees is equal to 2 pi. You will want to reference this example for the this diagram for the remainder of the notes as well as when you're working on the homework. Next, we are going to be looking at the steps for finding the trig ratios of a given angle given one trig function. First, you will use information to figure out which quadrant the angle will lie in. Then, you will draw a reference triangle and use the trig ratios to label the sides. Third, if necessary, you will use the Pythagorean theorem to find the missing side. And finally, find any remaining trig ratios, making sure to leave your answer in a simplified radical form. So to start, I have the fact that sine of theta is equal to 1/3, which is a positive fraction. If I look at the diagram on the top of my page, sine is positive in quadrant 1, under all, and in quadrant 2, where sine and its reciprocal cosecant are positive. Sine is not positive in either quadrant 3 or quadrant 4. Next, I'm looking at cosine, and in this case, cosine is a negative 2 radical 2 over 3. The diagram on the top of the page only helps us with knowing where the trig functions are positive. And because we know that cosine is positive in quadrant 1 under all and quadrant 4 under cosine, that means that it must be negative in quadrant 2 or quadrant 3. Because both of these trig ratios are positive or negative in quadrant 2, we must draw our reference triangle in quadrant 2. Before continuing on and drawing your reference triangle, please pause the video and make sure you understand how I figured out in which quadrant the trig ratios were positive or negative, and how I knew that I was going to be drawing my reference triangle in quadrant number 2. After you have figured this first step out, go ahead and draw your reference triangle. Remember that your reference triangles are always drawn by shooting out into the quadrant and then back up or back down to the x-axis. This forms my 90 degree between the vertical and the x-axis, and my angle theta is the one closest to the origin. From here, I know that opposite theta is going to be my opposite side. Across the 90 degrees is my hypotenuse side, and the side along the x-axis will be my adjacent side. Using the diagram above, I also know that my opposite side should be a positive value, and my adjacent side will end up being a negative value. For these problems, your hypotenuse will always be positive. Now I'm going to look at filling in the missing side lengths. For sine, we know that this is the trig ratio of opposite over hypotenuse. So along the opposite side, I will have a length of 1, and along the hypotenuse, I will have a length of 3. Step 3 said to use the Pythagorean theorem to find the missing side. Because you're given two trig ratios, and we know that cosine is adjacent over hypotenuse, instead of using the Pythagorean theorem, I can simply fill in that my missing side is negative 2 root 2. I can also confirm that the hypotenuse is, in fact, a length of 3. Now that we have completely drawn our reference triangle and filled in the missing sides, we can use it to find the remaining trig ratios, making sure to leave our answer in simplified radical form. We already know sine and cosine, which means next we need to figure out what tangent of theta is equal to. Tangent is the opposite side over the adjacent side, which means we have 1 over negative 2 root 2. However, the instructions said to leave our answer in simplified radical form, which we know means that we cannot have a radical in the denominator. This means we must first rationalize this fraction. To do that, I need to multiply by the square root of 2 over the square root of 2. Then I can multiply across to get 1 root 2 over negative 2 root 4. Because root 4 is a perfect square, I can simplify it to become a 2. So in the denominator, I have negative 2 times 2. In the numerator, you can either leave the 1 in front of the radical or just write root 2. Negative 2 times 2 gives me a negative 4. However, you want to either put your negative out front or in the numerator. And this will give us our simplified fraction for the tangent of theta. Now that we know all three original trig ratios, we must next look at the reciprocal trig ratios. So first, let's look at the one that matches sine, which is cosecant. Cosecant of theta can either be found by taking the hypotenuse over the opposite side or by flipping your original fraction for sine. That gives us 3 over 1 or just 3. Next, we'll look at the trig ratio for secant. Secant is the reciprocal ratio for cosine. So I can find it by either taking hypotenuse over adjacent or by flipping that fraction to get 3 over negative 2 root 2. And just like our tangent, we must next rationalize the denominator. So again, I'm multiplying by root 2 over root 2, which will give me 3 root 2 over negative 2 root 4. And in the denominator, I can simplify the square root of 4 to be a regular 2. So I have 3 square root 2 in the numerator. 2 times 2 gives me 4 in the denominator, and once again, I'm going to put my negative out front or in the numerator. Our last trig ratio matches up with tangent, and that is cotangent, so I can find it by either doing adjacent over opposite or by flipping the original tangent fraction. So I get negative 2 root 2 over 1 or negative 2 root 2. Before moving on to the remaining examples, please pause the video one more time and make sure that you understand where I got each part of this problem. When you're done, flip over to the next page. We are going to complete example 2 using the same 4 steps that we used on the previous page with example number 1. For example number 2, we are first given that sine of theta is less than 0, which means sine of theta, or sine, is negative. Our chart on the front only tells us when sine is positive, and we know that sine is positive in quadrant 1 and in quadrant 2. And if it's positive in quadrant 1 and 2, that means it must be negative in quadrant 3 and quadrant 4. Next, we are told that tangent of theta is equal to negative 8 over 7. Again, the diagram on the front tells us when tangent is positive. So we know that tangent is positive in quadrant 1 and quadrant 3, which means it must be negative in quadrant 2 and quadrant 4. Based on this information, we know that we are drawing our reference triangle in quadrant number 4. To draw our reference triangle, our terminal side is going to shoot out into the quadrant and then back up to the x-axis, forming a 90-degree angle. Our reference angle will be located near the origin. From here, I can label my opposite side, my adjacent side, and my hypotenuse. Looking at the diagram on the previous page, I know that in quadrant number 4, my adjacent side will be positive and my opposite side will be negative. Next, I can go and look at the information I'm given about tangent of theta. Tangent is the opposite side over the adjacent side. So I know that negative 8 is my opposite side and 7 is my adjacent side. I don't have a trig function to help me with the hypotenuse, therefore I must use the Pythagorean theorem. So one side squared plus the other side squared will be equal to my hypotenuse squared. So I get 49 plus 64 is equal to the hypotenuse squared, or 113 is equal to the hypotenuse squared. And in order to get c by itself, I must take the square root of both sides. Because 113 does not contain any perfect squares, it cannot be simplified and therefore gets left underneath the radical. Now that I know the length of all three sides, I can go ahead and complete the remaining trig functions. Even though we see sine in the original problem, we are not given its trig function, which means we still need to find it. Sine of theta can be found by taking the opposite side over the hypotenuse. Then, because I cannot have a radical in my denominator, I must rationalize this by taking the square root of 113 over the square root of 113. This simplifies to negative 8 root 113 over 113. Next, I will look at cosine of theta. Cosine of theta is the adjacent side over the hypotenuse. So once again, I'm finding that I need to rationalize by multiplying by root 113 over the square root of 113. This gives me 7 times the square root of 113 over 113. Tangent was given to me in the original problem, so I do not have to list it as part of my answer. So now I'm going to look at the reciprocal trig functions, starting first with cosecant. Cosecant can be found by taking hypotenuse over opposite or by flipping the original sine trig ratio. So root 113 over negative 8. We don't have to rationalize this answer, however, you should not leave negative numbers in the denominator, so I'm going to pull the negative out front to get negative root 113 over 8 as an answer. I'm going to do the same thing for secant of theta. Secant of theta can be found by taking my cosine function and flipping the fraction. In this case, I don't have anything to simplify, and I get my answer. The last one is cotangent. Cotangent of theta can be found by flipping the original tangent fraction, so 7 over negative 8. And once again, I just want to make sure that the negative is not in the denominator, so I pull it out front. This completes all of example number 2. Please pause the video and make sure that you understand each part of example number 2 before looking at example number 3. For example number 3, we are first given that cotangent of theta is equal to 12 over 5. Cotangent of theta is the reciprocal of tangent, and we know that tangent is positive in quadrant 1 and quadrant 3. That means that cotangent will also be positive in quadrant 1 and in quadrant 3. Next, I'm looking at the fact that theta is between pi and 3 pi over 2. Flip your note sheet back over to look at the diagram on the front page. If we look, pi is located at 180 degrees and 3 pi over 2 is located at 270 degrees. I want the quadrant located between those 2 points. Quadrant 3 is located between pi and 3 pi over 2, so this has to be quadrant 3. Based on this information, I'm drawing my reference triangle in quadrant number 3. That means that I need my terminal side to shoot out into the quadrant and then back up to the x-axis. My reference angle is that near the origin. I can also go and label my opposite side, my adjacent side, and the hypotenuse. Looking at the diagram on the front, I see that both the adjacent side and the opposite side should be negative. However, if I look at my function for cotangent, which is going to be the reciprocal of tangent, so adjacent over opposite, both those side lengths are positive. And that's because if I take a negative 12 and divide it by a negative 5, it will simplify to a positive 12/5. However, when I'm labeling my reference triangle, I want to make sure to include the negative both next to the 12 and next to the 5. We now complete the Pythagorean theorem to find the length of the hypotenuse. We have negative 5 squared plus negative 12 squared is equal to the hypotenuse squared. So 25 plus 144 equals c squared, which gives us 169 equal to c squared. If I want to get c by itself, I take the square root of both sides and I find that c is equal to 13. That gives me the length of my hypotenuse. For these problems, your hypotenuse will always be represented with a positive number. Now that I know the length of all three sides, I can look at writing down my remaining trig functions, starting with sine of theta. Sine is the opposite side, which is negative 5, over the hypotenuse, which is 13. And I don't need to simplify this function. Next, I have cosine of theta. Cosine can be found by taking the adjacent side over the hypotenuse. And tangent of theta is found by taking the opposite side over the adjacent side. And because I have a negative divided by another negative, my answer ends up being positive. Now I can start to look at my reciprocal trig functions, starting with cosecant. Cosecant can be found by taking hypotenuse over opposite or by flipping my sign fraction. Once again, I want to make sure not to leave the negative in the denominator, so I get negative 13 over 5. Secant of theta is found by taking 13 over negative 12. And again, I'm just going to relocate the negative from the denominator to out front of the fraction. I don't have to list cotangent of theta because it was given to me in the problem. Please make sure that you understand each part of this problem before looking at the next example. We will be skipping example number 4, so when you're ready, please look at example number 5. For example number 5, we are given that cosecant of theta is equal to 3 over 2. Because cosecant is positive, and because it's the reciprocal of sine, we know that it is positive in quadrant 1 and quadrant 2. We also know that the only quadrant that appears between 0 degrees and 90 degrees is quadrant number 1. Which means you are drawing your reference triangle in quadrant number 1. In quadrant number 1, the terminal side will shoot out into the quadrant and then back down to the x-axis, giving you a 90-degree angle. Your reference angle is located near the origin. From theta, I can label my opposite side, my adjacent side, and the hypotenuse. And looking at the diagram on the front, I know that both the opposite and the adjacent side will both be positive. Because cosecant is a reciprocal of sine, I know that it is hypotenuse over opposite. So my hypotenuse is 3, and my opposite side is a positive 2. I'm going to use the Pythagorean theorem to locate the length of the adjacent side. When using the Pythagorean theorem, I want to make sure that the hypotenuse, the side across from 90 degrees, ends up on the side of the equation by itself. So I get a squared plus 2 squared equals 3 squared, which will simplify to a squared plus 4 equals 9. Solving for a squared gets me a squared equals to 5. And taking the square root gives me a is equal to the square root of 5. Because the square root of 5 does not contain any perfect squares, I cannot simplify it, and that is the length of my missing adjacent side. Now that I know the length of all three sides, I can look at setting up my trig ratios, starting with sine of theta. Sine of theta is the opposite side over the hypotenuse, so I get 2/3. Cosine of theta is the adjacent side over the hypotenuse, so I get root 5 over 3. Tangent of theta is the opposite side over the adjacent side, which I need to rationalize by taking root 5 over root 5. So I get 2 root 5 over 5. Next, I must look at my reciprocal trig functions. I already have cosecant listed, so I can move on to secant of theta. By root 5 over root 5 to give me an answer of 3 root 5 over 5. Lastly, I have cotangent of theta. Cotangent can be found by taking the adjacent side over the opposite or by flipping the tangent fraction. You have now completed all of the examples in this video. If you are still confused about any part, please rewind the video and listen to that section again, especially going through the diagram on the first page. Now that you have gone through all the examples, you can now try the homework problems on your own. If you are still confused about any part, please rewind the video and listen to that section again, especially going through the diagram on the first page. Now that you have gone through all the examples, you can now try the homework problems on your own.